It's been a few days since we looked at isotopes and we predicted what type of nuclear decay an isotope might go through and writing the equation. So let's do this for a little practice. Hit pause here in a few minutes or a few seconds, and I've given you three isotopes at the top of the screen. Find the neutron to proton ratio for each of those three, and then try to figure out which type of decay it might go through: positron, beta, or electron capture. For these examples, I left alpha off because alpha is pretty much the easiest one. So hit pause and see if you can find the ratio, and then guess which one it will be before I give you the answers. Okay, so on the screen I've put the neutron to proton ratio for each of those isotopes. For thorium-234, the neutron to proton ratio is 1.6. Well, to figure out what it's supposed to be, let's come down here to the graph. And thorium has 90 protons. So it is above our zone of stability. And this ratio right here is about 1.55 or something like that. It's pretty high. So even though we're out here where alpha decay normally occurs, in this case we're with an isotope that's at 1.6. It's too high. Remember, alpha wasn't an option for us. The important thing is here is this nucleus has a high ratio of neutrons to protons. For nitrogen, nitrogen has an atomic number of 7, so we come down here and we're in this region. It's supposed to have a ratio of 1 to 1. Well, we have less than that. So this isotope has too low of a ratio. And then for rubidium-73, with atomic number of 33, we come up here and approximately over, and we do the calculations. And of course my lines here are kind of crooked, but just say 40 divided by 33. That's pretty funny. I got it just about what it is. It's really supposed to be around 1.2 at this point. We're right there at it. Some people would say 1.2 to 1.4 in this area. It just depends. Again, there's a lot of gray areas here. But we're going to say that it's too low. Or at worst, it's right there on it. Alright, so anyway, we have a high, a low, and a low ratio. Which one of the three types of decay methods did you say thorium-234 was going to do? If you're too high, then your only option is really beta. Because beta serves to raise the number of protons, which will lower your ratio. The other two, positron and electron capture, both do the opposite. They want to increase your ratio by making neutrons. So it's a matter of where on the atomic number list, on the x-axis, these two fall. Remember that positron usually occurs down here at the low end of the curve, while electron capture is out here with a bigger nuclei. So nitrogen-13 is going to undergo positron, and then that leaves rubidium-73 for electron capture. Okay, so go ahead now and just write out the nuclear decay equations for each of those three. Hit pause, and then we'll go over them together. Okay, here's the equation for thorium-234 undergoing beta decay. We're going to undergo beta decay, so we'll kick off a beta particle. Conserve the mass across the top. 234 equals 0 plus 234. So the mass doesn't change in beta decay. 90 equals negative 1 plus, so 91. Remember, beta decay always makes you go up the periodic table. And that element is protactinium. So there's the beta decay equation for thorium-234. All right, the next one was nitrogen-13. And we decided that nitrogen-13 was going to undergo positron emission. Remember, positron is a positive proton. Sorry, positive electron, excuse me. That's what I get for talking while drawing. So there's our positron. Let's conserve mass. 13 equals 0 plus. So the mass number stays the same. And charge, 7 equals 1 plus 6. Recall that positron emissions lower the atomic number, and that's going to give us carbon-13. Finally, we have rubidium-73, and we decided it's going to undergo electron capture because it has a bit of a higher, or a bit of a heavier nucleus, more positive charge. So let's add that electron to this side of the equation. It doesn't have to be pretty, thank goodness. All right, let's conserve mass. 73 plus 0 equals 73. 33 plus a negative 1 is a 32. So electron capture does the same thing as positron emission. It makes the atomic number go down. So look at the periodic table, and I believe that is germanium-73. Okay, we'll do more of these in class, but if you're still not really getting it at all, let me know and we can do more of these.